So
I had two titles. None of these are the title that I submitted, but so I have a caveat emptor. So I finished writing these notes, and then 15 minutes later, I was like puking my guts out and feeling horrible. I don't know what this is about the quality of the talk that I wrote, or my state of mind when I was writing it, but hopefully,
so it's good that you finished before.
Good, yes. Hopefully it'll be okay.
Okay.
We've had a lot of slides, and we've had a lot of equations and a lot of discussion this conference, and this is basically the last talk. Also, thankfully, Matteo already gave his talk. So if I were to talk about my research, I would just give Matteo's slides, but replace Baco with Emulus everywhere because we've been writing and scooping each other for the last 4 years. So I actually figured that it might be nice to have this audience to kind of proselytize a little bit, be a zealot for this other picture of a large-scale structure formation, which is this Lagrangian picture, which I wrote a few of the historically relevant papers. So this dates back to Zalgovich in 1970. You know, Arnold, like Vladimir Arnold got involved and did a very beautiful work categorizing the singularities that form in the Zalgovich approximation in 1982. All the way down to, I would say, the modern formulation dates to these two Matsubara papers from 2008. And the idea is really to just explain why this is different, why this is qualitatively different, what we can learn by thinking about structure formation in this picture. And my goal is to do one calculation. And hopefully it's the one calculation that everyone will follow, but I think it's a very interesting and insightful one. And with luck, I will do two calculations. So we'll see. But I mean, yeah, so for right, the broadest possible context, the idea is just structure formation historically has challenges that organize themselves in two fronts. So on the one hand, people are really interested in turning this initial distribution of matter at very high redshifts, as probed by the CMB, that's very Gaussian, into this very late time distribution of dark matter. So specifically, this is a zoom in from the illustrious TNG simulation around what the largest cluster ends up being. But the point is, even in the initial conditions, this is not showing temperature, it's showing over and under densities. You can just by eye see that there's a very clear, very strong correlation between where the overdensities in this Gaussian field are and where you actually end up seeing structure. So this tells us that there should be some very good way to have an analytic understanding, tractable understanding of this process, because at least on these scales, you know, this is about 30 megaparsecs, they're very spatially correlated. Of course, the other challenge, which is relevant for people doing galaxy surveys and clustering specifically, is how do you relate this distribution of dark matter that's very nonlinear, very non-Gaussian, to the distribution of galaxies that maybe might look something like this. And so a diagram that looks like this, but gives it another axis that I really like, it dates back to this paper from Fujita and Blah in 2020. So they point out that really there's sort of two pictures of structure formation. Two pictures, two ways of making this connection across these gaps. And so the standard one is the Eulerian perturbation theory picture, as Fujita very, gracefully explained in his talk last week, where you basically write mass conservation for this fluid, and you write momentum conservation for this dark matter fluid, where it interacts only through its own self-gravity with no pressure a priori, and you just let these quantities evolve. And so you go from some early, very linear Gaussian distribution to some very late time distribution of dark matter. This is nonlinear, this is non-Gaussian. And then you basically say, oh, okay, my galaxies today in simulations kind of look like they really trace my galaxies or my dark matter distribution in simulations. And so I will just start to write a statistical description between this field here and this field here. And I will write a perturbation theory for this. But it actually turns out that since this is a fluid dynamics problem, and fluid dynamics always admits two frames of references, the Eulerian and Lagrangian frame of reference, you can also reformulate this problem as this Lagrangian picture, where what actually ends up happening in practice is that you connect the linear distribution of matter to what's called the distribution of proto-halos or proto-galaxies. So the fact that this does not look too different from this, in some sense implies that a lot of the information about this distribution is already encoded in this initial linear distribution. And so you can try to find statistical mapping that holds really only at early times. And then you just used this notion of these Lagrangian displacements to just move this fluid of this proto-galaxy fluid to late times and get some. So physically, right, what is the sort of Eulerian versus Lagrangian picture of structure of fluid mechanics in general? Eulerian fluid mechanics is the lab frame, right? So you're basically, you might have some fluid flow that's going like this, but then you're drawing some voxel somewhere, some region, and you're asking basically, okay, what is the density at this region, or the density contrast relative to the average at this region? What is the velocity divergence flowing through this region? What is the pressure, maybe if you have a pressure, or what is the temperature if you have some equation of state? But you're doing this at every cell, and you're writing equations of motion that connect these quantities from one cell to the other cell. On the other hand, what the Lagrangian picture is doing is really you're actually just putting down several different particles and letting them flow. And so you're not asking basically what is happening at here at any given point, but I had a particle that was here, and then it moved to here and moved to here, passed through the cell and then moved out, and you're tracking each of these individual particles and their properties and sort of taking a statistical understanding. Since you know what every single particle is doing, you understand what this fluid is doing in aggregate. And so this is what the Lagrangian picture of structure formation is. And so actually it turns out in cosmology, this is pretty simple to write down. Everyone who's taken physics 1 can do this. The dynamics of a Lagrangian particle, of a dark matter element, of a fluid element, are just going to be given by Newton's second law. And so basically what you're going to say is for every particle, maybe it started here at some position Q, maybe it ends up here at some position X, and I'm going to just say that all of its trajectory is defined by some vector, which I will call psi, which is the displacement. And so all that I'm saying is that this particle's dynamics from the one that arose at this position Q at a time t are just its initial position plus this displacement psi, Q, and t. And then you say, okay, but this is just a particle that's just evolving under gravity. So the equations of motion are just going to be Newton's second law, but in an expanding universe. And so really what you end up writing in sort of the, once you take sort of the right units, et cetera, for time, people normally do this in conformal time just because it simplifies a little bit, is just something that looks like this. And if people can't see my writing or can't see my slides or want me to go there, let me know. But basically every single particle then, what you're really doing is you're just writing Newton's second law, evolving according to some potential that's sourced by the density of all of the other particles that you had, but you have some friction term because the universe is expanding. And this is what you try to solve, actually. And this is really the problem that Zadovich was trying to solve. And so what Zadovich did was basically write something very similar to this down. And then he just took this equation. He said, well, Q is just some index that labels what particle I'm tracking. I don't actually care about it that much. It's just some initial reference frame that I can specify and I have full control over. So let me try to get at an equation for what these displacements are. And so if you just basically plug this in, quite literally, is it okay if I use this part of the board? Are people fine with that? Okay. Right. And so what you basically arrive at, if you plug this in, take some divergence, is some equation that will look like this. And then you use the Poisson equation over here. And so this gets you a little bit closer to the answer, but this is still not really great. Because what we're really interested is in finding out what the solutions for this psi of Q are, where this is our initial condition. This is some derivative in terms of X. And the density, of course, is always defined in terms of this late time quantity as well. And so there's still some operations that you have to do to get to an equation that you can massage, something that looks like the Eulerian equation of motion over there that you can then solve perturbatively order by order.
Sorry, the last question. X is just the coordinate of the system.
X is the coordinate of one particle. So I'm writing the equation of motion on a particle by particle basis.
Okay.
So this would be like X of Q, really. Yeah. And so the second ingredient that you need is to basically consider the following. If I just specify this initial fluid, my initial distribution of particles to be uniform, there's no clustering in them at all, and I know that they're evolving smoothly, as long as my particles don't cross each other, then the mass is going to be conserved as I basically distort the cell that it was in and displace it and move it out. And so what you can also do is assume mass conservation. And you can basically write the following relation, that this average density of the universe at very early times in this Lagrangian coordinate system, the mass that I have in some small cell of D3Q is just going to be some late time density in my late time cell for this coordinate system. And so this actually helps a little bit because now you see that we have some expression for what the density at x coordinates is, which is what ends up showing here. And we just have to figure out what this Jacobian remapping is between the two coordinate systems, this Lagrangian and Eulerian. And again, well, okay, let me do some steps and then we can go a little bit forward. I mean, what you can then do is just realize that you just have to figure out what this Jacobian between the Lagrangian and initial coordinate system is. This is also derivative that all of us who have taken calculus, calculus 3, I guess, can do, right? But it's just dx dq exactly gives you this mapping between the two coordinate systems. And so what you really find is that you have some Jacobian, some inverse Jacobian determinant is just going to be equal to 1 plus this late time density field. And this Jacobian specifically, and I'll write this here because I'll use it a lot, I guess, is just given by and so this is interesting, and there's already a lot of qualitative things that you can learn about large-scale structure just from looking at this. It actually turns out if you analyze this more carefully, you can figure out what are the first kinds of structures that are going to form, if they're sheets, if they're filaments of dark matter, if they're halos of dark matter, depending on the properties of this Jacobian. Also, interestingly, this can go singular at some point. And when this goes singular, the density is going infinite. This is basically when you have two shells of dark matter that have crossed into each other, the density blows up. And so this is when this approximation formally breaks down. But this is kind of interesting because now I can plug this back in and I get at the equivalent equation of motion for Lagrangian perturbation theory that I had, the Eulerian one. And so you can do some algebra to get to this LPT master equation. And it's really ugly, but bear with me. And this is it. And so this is what Lagrangian perturbation theory ends up being. It's instead of solving for finding the F and G kernels that order by order give you the solutions to the density and the velocity divergence in our Eulerian perturbation theory, what you're basically doing is just expanding this Jacobian, which only depends on Q because it only depends on the Hessian of that displacement, on the gradient of that displacement field. So this depends on Q, this depends on Q, on Q, on Q, everything now depends on this initial Lagrangian coordinate system. You expand this order by order in these displacements. You'll generate some differential equation for the time evolution, some mode coupling for how the second order solution depends on the first order solution, but you're done. And so this is what basically took people quite some time to figure out how to do properly. But what Arnold did, what Zldovich did and what he was interested in doing was just linearizing this. And so if you linearize this,
Linearizing the displacement.
in the displacements. Really, he's linearizing in the divergence of the displacements. And so if you do this, what you get is an equation that looks like this. And anyone who's taken an intro cosmology class should be able to read off what the solution to this is immediately. This is literally the equation of motion for the dark matter density contrast in linear theory, if you identify the divergence of this displacement with the density contrast. And so what you actually find is that the linear solution for the equation of motion of dark matter particles is stupidly simple, but not stupid. The time evolution is just given by the same growth factor that you have in lambda CDM, plus some initial kick that you still have to figure out, add some initial time that you gave to this initial coordinate system. And it actually turns out, just for time, I'll skip this, but you can also use the linearized continuity equation up there, that mass conservation term, to realize that this initial kick is just given by the initial density fluctuations in the very early universe. And so what you get is that the linear displacement is just intimately related to The initial kicks that dark matter particles get in the very early universe is just related to the initial distribution of density fluctuations, but now they're all just going to move straight. And so this is actually really non-trivial, because it turns out that the relationship between the density at late times and the displacements at early times is really given by this Jacobian in some way. So this is some really nonlinear relationship between the late time density distribution and the early time displacements. And so the way that you can see this is that if you go back to this mass conservation term, you can effectively rewrite this in the following way. And I can motivate it, or I can explain it, but you can, if you have questions, but you can also just believe me, you can effectively rewrite this Jacobian as an integral over the following delta function. So you're just basically saying everywhere that I had some initial fluid element, I'm just moving it to late times, summing them all at that late time point that they're at, and this gives me the density field. And then if you rewrite this delta function as its Fourier representation, you will get that basically the Fourier space density field at late times is equal to and so this is actually already a very, very non-trivial statement about the relationship between displacements and densities in Lagrangian theory. Because first of all, this actually didn't assume any perturbative approximation for psi. So this is a non-perturbative description of if you have displacements, you get a very nonlinear, very non-perturbative density. Not only that, but if you use the Zadovich approximation and you say that my displacements are really just given by my initial density fluctuations, then what I get is that my late time density field is not just some growth factor times my linear density field and nothing happens. It's actually some exponential resummation of my early density field. And not only that, but this also explains why the log normal approximation works so well in cosmology. Because if you actually look at this a little bit more carefully, this is a normally distributed random variable. And so what you're really saying is that the late time density Fourier modes are just some exponential, some variable that's normally distributed. And so this is sort of morally explaining why the late time density field is log normal.
Why that one should be Gaussian distributed?
Because this is given only by the early density field, which is Gaussian. And so it's, all of the Fourier modes are independent and they're all Gaussian. So this has every Fourier mode being Gaussian. The Fourier transform of this is also just going to be Gaussian.
It is somehow like served in higher orders, just something that only should happen in like first order. Like relation between psi and
This one is only at first order.
in higher orders these things.
Then you need 2 LPT, 3 LPT, etc. You can write it down. You can just solve those equations. I can write down the second solution if you want, but it's not very illuminating.
But it's not there.
Yeah. I mean, it is kind of illuminating. The second solution will depend on delta squared, and it'll depend on the tidal field squared as well. So you have tidal field information at second order in the LPT solution. So like this is kind of stupid, right? All that we said is that what if we, instead of just letting the density field scale in time, but remain the same spatially, what if we just instead let every particle move straight in some way? Then you actually find some extremely nonlinear relation between the late time density field. And this is actually something that Zadovich realized all the way back when. And so, you know, this is his original paper. And then with Shandaran, who was one of his students in 1989, they wrote this really beautiful review of modern physics, where they sort of connect the large-scale structure of the universe to turbulence and many other fluid dynamical effects. And so first in the abstract, Zadovich already says, you know, the solution is qualitatively correct even when the perturbations are not small. So this is something very important. Even back then, he recognized that this was a perturbation theory in the displacements, but not necessarily in the densities, which is what Peebles was doing back in the day. So this is, you know, very qualitatively different. But in this review article, they point out that really the way you should be thinking about structure formation is if you've had many, many, many light rays that were parallelly propagating, and then they all get scattered by some initial corrugated lens, which looks like this density distribution at very early times. then all of the light rays are going to be bent in some non-trivial way. And structure formation is just if you have some screen that you're moving back and looking at the patterns that the light rays form. And this looks like this. This is the exact same math behind why you get caustics in a swimming pool. So, you know, this is, and that you get all of this very nonlinear structure from this linear solution is kind of crazy. And so then you might also be saying, okay, you're like waving your hand and saying that this is true. In practice, how well does it hold? And so what you can also imagine doing is just running a full n-body simulation on your computer, which is solving that Newton's law for every single particle and will take 10,000 CPU hours. Or you can run a Zadovich displacement, which is normally how we initialize n-bodies, to later times. And this is what the density fields look like, right? So this took 1 CPU hour on my laptop. This took 10,000 CPU hours in some Quixote simulation. And you can see that qualitatively, the large-scale structure of the universe in both of these simulations is extremely similar. And this is just literally applying this equation over here, but where I kept this term to be the linear one. So this is like, just, to me, just extraordinarily strikingly powerful. And sort of why I became a seller. But, you know, we're not just here to make pretty pictures and swimming pool costumes. To some level, we also want to calculate things. So,
This statement is non-perturbative, but does it break down at some point?
it does. So it will basically break down when this Jacobian becomes singularly valid, when the determinant goes to 0, basically.
So that's shell crossing.
At shell crossing, yeah. So basically, when you have two streams of dark matter that actually cross, what the Zadovich approximation states is that they will just cross momentarily. The density becomes infinite, but they don't matter, and they will just keep flowing past each other. And so this is why the structures here look fuzzier than in the real universe, because particles can't ever turn around. There's no gravitational attraction, they're just going straight. In the real universe, not only you have gravitational attraction, the closer you are, the stronger it will be, and so you can actually have orbital effects, scatters, things like that. So this is something that is not contained in LPT at all, because LPT relies on this expression that will just break as soon as this Jacobian becomes
So you're stopping the simulation, you're on your laptop, you're stopping before caustics or something.
No, I run it even past. So the Zadovich approximation will get worse over time as this shell crossing starts to happen. But really what you can see happens is like the halos, you don't actually get halos here, right? But the halos just look kind of fuzzier than the ones in the actual simulation.
And that's because
instead of the particles turning around where you had some confluence of flows, instead of them getting wrapped up into something, they just pass each other. So it puffs out a little bit.
One question. So is it the elevation that fails when you have shell crossing, or it's the whole perturbation theory?
It's all of the current way we formulate Lagrangian perturbation theory that fails at shell crossing.
Right, so Zadovich should fail before, right?
Zadovich fails before. I mean, so this is kind of interesting. It fails before, but at least in terms of this correlation with the large scale density field, it still works very well. It does a very bad job of, so even though this distribution looks non-Gaussian, it does a very bad job of predicting what the skewness of this field is, for example, because it doesn't have the nonlinear growth, which is the #1 driver for skewness, actually. All that this can do is basically reshuffle the initial 2-point power into other functions in some bad way. It's not quite correct. And the way that you can see this is actually if you take this approximation, you plug it in here and you expand this exponential. At linear order, you recover the linear density field. So at linear order, they're sort of exact. But at second order, you actually get something that doesn't look like the F2 kernel, right? You get something that can only look like delta squared. You don't get and the displacement term. You don't get anything that looks like the S squared tidal term. And so this is actually what gives rise to what people call transients in n-body simulations, because you initialize it with a density field that has the wrong F2 growth, according to the standard theory. So there are some caveats, but it's, you know, qualitatively, it's still impressive how good it is. Yeah, is there any other questions?
That aspect of breaks down.
Yeah, so the shell crossing is really kind of, it's a hard limitation of this formulation. A lot of people are trying very hard to figure out alternative ways, but it's very difficult because fundamentally, then you have to basically imagine tracking fluid dynamics, what they call multiple streams at the same time, and analytically, that's just very difficult. So, okay. So I guess the other thing that's worth mentioning is, what do I want to say? Oh yeah, so also I said this looks not log normal, but it's actually not really log normal. There's a really nice paper by Shendarin also and Lev Kaufman, where they calculate actually the exact PDF of delta conditioned on the Zadovich approximation. And it's not exactly log normal, but they do work it out. It's like a really tour de force in probability theory. It's really cool.
By the way, something I was always puzzled about. I mean, people talk about those marked transformations, right?
mhm.
And it's kind of log marked transformation that people have. I mean, I find this to be very attractive, right? This is just a Zadovich.
Yeah.
Why don't we play with the?
Well, the way that you can imagine, so maybe not with like log marked transformations explicitly, but this explains why reconstruction works so well also, right? Because to some extent, you know, you're basically saying that one of the largest parts of the decorrelation between the late time density field and the initial conditions field is just captured by this phase that you're introducing exactly to move everything back. And so that, you know, motivates why reconstruction works so well. With marks, it's a little bit tricky. But yeah, it's worth thinking about a little bit more. Actually, there's a really nice paper by Haruki Amina and Martin White on marked power spectra in LBT recently that went into a lot of detail. Okay, so now I'm going to skip over a lot of algebra because what we want to calculate are summer statistics. And the point is that even the power spectrum is kind of non-trivial here. But if you just take this expression that I gave you here, and then you basically calculate, you know, delta K, oh, sorry, delta K prime, and I remove my direct delta function here, you basically get the following expression. And this starts to show why people very quickly abandoned LBT to some degree. So when you try to calculate even the power spectrum in this theory in full generality, you basically find that the power spectrum is actually already given by some expectation value of some exponential of two, you know, pairwise separated displacements. And so this is already a very, very tricky thing to calculate. It's already very, very, very nonlinear. And so what a lot of people did in LBT for a very long time is to just say, oh, okay, I'll just, you know, expand this out in my exponent. But then people very quickly proved that this order by order gives you the same exact result as earlier in perturbation theory. So
We don't use this first order, put it there, calculate the two-point correlation conditions in the linear Zadovich approach.
so you can, but then you would have to figure out how to do this, which also took people some time.
But that's the delta, right? And then
This is delta, but this is the correlation of e to the I k dotted into some Fourier transform of differences of deltas.
yeah, the K cancels though. If you put the
No, okay, so good.
if you put psi in the equation above,
It doesn't cancel.
no,
Because this is psi of q. This is the Fourier transform of that psi over there.
ah
So there's actually, this k is a k
ah
that corresponds to the Lagrangian q. And this k here is the conjugate to the late time x.
so there are two. Okay,
So it's actually very, you know, it's kind of subtle.
Sorry, Nick, I don't know what Q2 and Q1 there?
Yeah, so that's because I was looking at the correlation function of a density field defined as some of Q1 and another one that's Q2. Right, these are just the Fourier conjugates that I had.
Right, but there's only one integral over Q.
Yes, because what you get is an integral over Q1, Q2. And if I shift into
Q
the
now is Q2 minus Q1.
exactly, because you can shift into the frame of Q2 plus Q1 and Q2 minus Q1 and do the Q2 plus Q1 analytically. And this result is actually very interesting because this is like fully Galilean invariant, right? You're expressed everything only in terms of things that are differences of displacements. So if you do some sort of, you know, Galilean boost, you actually immediately cancel out anything and the answer stays the same. Okay, so people had written this down and you can find this written down in like 1998. There's a paper by Andy Taylor and Andrew Hamilton that writes this down. The same Andrew Hamilton who did FFT log and then left Cosmology forever. And they actually analytically calculate some cases, but this is very true. And really took into this Matsubara paper from 2008 to learn how to do this. And so, okay, what we can imagine doing first is expanding this order by order in this difference of displacements. But when you're doing some sort of expansion, you have to ask, is this thing even small, right? And so what you're sort of asking is whether the variance of this k dotted into this delta field, this variance of displacement is small. And so the quantity that you kind of want to be looking at is whether k squared times this. Okay, great. And so what you're really asking is whether this, in normal or Lorentz perturbation theory, we're asking whether the variance of the density field is small. This has some scale, so really you have to ask at what case does this product, which is dimensionless, actually small. And so really, if you look at this looks something like the following. So we use P here, so P. One problem with LBT also is that Q's, which are normally momenta, become coordinates. And so we lose a second momentum that we really like. So because this is not the variance of a displacement, what's kind of interesting is that this quantity over here is actually very, very sensitive to the IR scales. And so the quantity that you want to be small is actually primarily dominated by very large scales where you thought your theory should be under control. And so
The delta is Gaussian.
the delta, this delta is not Gaussian.
No, but the big delta.
This delta, yes.
You can assume that after expanding or.
Well, so if you could, and I'll actually show a way to just do it directly resummed, but this is what the consensus 2008. But what people did for a very long time was trying to expand this and calculate it sort of order by order.
So you expand it, can compute it order by order because it's Gaussian, then just resume it back. It's not that simple, right?
Not for all of those people. Yeah, I mean, historically, this is my understanding of how it's played out in reading the literature. But the point is that this is kind of, you know, k squared, and this number here evaluates to actually sort of 36 MPC over h. Oh, sorry, it's 6 MPC over h squared. And so even at k of 0.15, this is already order 1, right at around the BAO scale. And not only that, but most of this contribution is coming from very large scales. So when you do this sort of standard expansion to recover Eulerian perturbation theory, you're actually expanding in a quantity that's large. And so this is what gives rise to this problem with the BAO that people have talked about, of the IR resummation. These large scale displacements, which are actually Gaussian and you know exactly where they come from, you're saying they're perturbative and small, but they're actually not, right? So this is just something to keep in mind, and I will get back to in a second.
Because you can resum. It
Yeah.
doesn't matter if you can sum it, right? Because you resum it back to the exponential, it's large, then just merge.
Yes, yes.
That's what happened in the end.
That's where I'm going to, in one equation. Okay, so how do we resum this? Because clearly we shouldn't be expanding this. And this is what leads to this problem in SPT of basically the BAO is completely wrong in SPT if you've seen these plots before. Maybe I should have had a plot, but it looks really bad. Like the one loop power spectrum in SPT looks horrendous. The correlation function had like 2 bumps, for example. It really is like senseless. So what you can realize the following, as Gonzalo has pointed out, right? This is Gaussian. So this is really just some exponential of a Gaussian. That should be a very well understood distribution. And in fact, there's this theorem, which is this equivalent expansion theorem, which for the exponential of any random variable, this is really just given by the exponential of basically some form of a series of the connected moments of this random variable. And so it turns out it took until 2008 for people to realize that you could evaluate this correlator in this way. And for Gaussians, this is connected, so this truncates at second order. And so really what you basically get is just that that entire thing is really just equal to the exponential of 1/2 minus 1/2 of what basically looks like out k times this delta, right, squared. Like this. And so this is something that maybe we can evaluate more comfortably. Now, something that's kind of interesting, actually, okay, let me just write down what happens when you do this then. And so if you apply this theorem over here to that expression, you get the final equation, which is this power spectrum in the Zodovich approximation, which is equal to the integral of dt. So it's some Fourier transform of some function that is actually defined in configuration space. It's actually some sort of tensor correlated like this. And this might look kind of nasty, but it turns out it's quite a mess. And so what Matsubara did, which he was the first person to realize, is if you write this in terms of these displacements, and then you're squaring them, you're going to get contributions that are psi evaluated at itself. So it's zero separation, and psi evaluated at different positions. And so you get terms that are zero lag, that are just a constant and don't depend on Q, and terms that don't. And so this is Matsubara.
Okay, but this is only Zodovich, no? Because
This-
this delta, the capital delta is non-Gaussian.
Yeah, this is only in Zodovich, exactly. But this also tells you order by order, if you have a second order contribution, you can keep all the connected cumulants up to some order in perturbation theory, which this is a talk only about in Zodovich, but I can explain how you do this for other cases. But so what Matsubara gets is that this is equal to e to the minus k squared over 6 pi squared, the integral of dp, d linear of p, times the linear power spectrum of k, plus a correction, looks like 6 pi squared. So kind of interestingly, you basically get a resummation that turns into some Gaussian damping by exactly this factor that I said was small, or was large, but that you knew exactly. And so what this looks like is like this. And so what you can see is basically his calculus. So this is the ratio between the red is the ratio between the linear wiggle and the linear non-wiggle power spectrum. The green is what you get if you try to do, I think, SPT, if I remember correctly. And the black is the result of this calculation. So this, like, the oscillations are tracked much more carefully as a result. And this also explains the sort of phenomenological form that a lot of people had applied for this damping of the BAO feature in the original Boston. This gives you some a priori analytic understanding. There's a very big problem with what Matsubara did. He broke out linear invariance by doing this. And so people, some people were very happy. And the reason he did this is because he selectively treated terms that are adding at the same place versus terms that are at different places differently. And he resums only the parts that are zero lag. So the parts that don't depend on Q are in the exponential, and he expands the other terms. But this breaks out linear invariance of the expression. So let's not do that. But yeah, I'm sorry, let me see how I'm doing on time. Oh my God, okay. Look how this is gonna happen. Okay, but still, hopefully you can appreciate that even the power spectrum in this Zodovich approximation, everything should be linear, also predicts not only that qualitative structure formation is very good, but that something very non-trivial like this damping of the BAO is captured analytically to very exquisite levels. And again, everything is very treatable. This Taylor and Hamilton paper is really nice. That what they basically do is point out that in power law cosmology, you can evaluate this thing exactly, and you can evaluate this whole power spectrum exactly. And also, if you have some exponentially damped linear power spectrum, what you find is that the late time power spectrum goes as k to the -3. So even if you have linear power that is exponentially cut off, like some warm dark matter model, for example, after some scale, the late time distribution will actually not have that cutoff present. So this is also very non-trivial, and it's related to the formation of constants in these models. So all of this stuff is just contained in this approximation.
So the exponential side is this expression like of the wiggles, and the term inside is already the one loop, right?
So technically you would also have the one loop SPT contribution in here, but because I don't have non-Zodovich displacements, I only kept things that are that additional term is not related to SPT one loop.
So what's the second term you get inside?
It's from expanding basically the part that is not at zero lag to higher order.
How can I read it like intuitively?
It's effectively like, so this original Matsubara damping is actually too strong of a damping, right? Because normally you take the wiggle non-wiggle split and you damp only the wiggle. So here it's physically trying to correct for some of the over damping that his approximation does. But again, this is not fully correct. It's just the easiest way to see where this comes from.
So that integral converges.
Mm. Yeah. It does, right? Because this just goes as dp times p. P goes as p to the minus, the power spectrum goes as k to the -3. So it's just the integral of k to the -3 that converges.
This looks also pretty much this Martin Roche's Kochimaro resummation schemes, right?
Yes, very similar. Also not Galilean invariant.
Is it basically the same kind of?
It's a good question. I think yes, but I think what they try to do in their scheme is they try to write the SPT kernels and they try to identify within the like F kernels all of the like internal legs that you can close off to have like things that are like look like the linear power spectrum resummed, and then do that. But you get basically very similar answer.
So Nick, you keep coming back to the fact that this was breaking Galilean invariance.
Mhm.
Are you going to fix it next to us, or you're just measuring this and it doesn't really matter too much?
I mean, for the purpose of this
Thing to
talk,
do.
for the purpose of this talk, it doesn't matter. But I mean, I can tell you, this was done in this paper over here, this Carlson Reed white paper, which if you now try to Google, give some Fox News story about Tucker Carlson interviewing someone called Reed about white supremacy. So, anyway, no, so I can explain just for, okay, so basically what you do is just, if you just, up to here, you haven't done any breaking of Galilean invariance. And so whatever this function of Q is, which is defined as, you basically decompose this into the most general rotationally covariant indices that you can get, times some scalar function of Q, plus something that looks like this, times some function of Q. You know exactly what this is. So you can just figure out what X and Y are by solving the linear system of dotting K's and Q's into this thing. And then you get some analytic expression that you can then just solve. It's technically challenging because you have sort of band oscillations and things like that, but you can do it. And this gives the correct resensing. What the Carlson Reed white paper also does is point out a Galilean invariant way to keep higher order LPT contributions while still only resumming the linear part, the Gaussian part. So it's basically the right way. What are the right quantities to expand out of this exponential? Because if I had higher order things here that were non-Gaussian, they would show up here. But then the point of that paper is that you can actually keep this term in the exponential and you can expand out only the terms that are non-Gaussian, because the 2LPT correction divided by the Zadovich correction is very small. That's an okay quantity to expand it. So Zadovich is large, but we know how to do it. Okay.
So what K would expect this to fail?
Well, so actually this basically, so here the K scale, instead of being, again, when the delta is order 1,
It's not the 6 megaparsecs.
it's related to this quantity. This is at redshift 0 that it's 6 megaparsecs, but this is the right quantity because this is the velocity dispersion of these displacements. So at smaller scales, this velocity dispersion is basically going to be dominated not by the linear flows, but by nonlinear gravitational attraction. Okay. So in my like, yeah.
I'm sorry, I
Mhm.
missed some part of it. So there is a linear invariant resummation here, or?
Yeah, there is. So the way that I wrote it down here, notice that everything is always defined in terms of the actual difference.
I see.
So the point is, if you take the Q goes to 0 limit of this quantity, they cancel each other out. But the way Matsubara did it the first time, he only identified one of the Q equals 0 quantities, expanded it, that was non-zero, and kept the term that wouldn't cancel that in the exponent. So, okay, so. Yeah, so this is a lot to do. This is just the first set of results, but they're, I think, very non-trivial.
But for instance, compare this with Halo fit. See how well.
This doesn't work, right? So there's only linear. So this looks like the linear power spectrum still, but then with a Wiggles depth.
So this doesn't really work.
Well, I mean, depends what you call work, right? So the power spectrum looks like the linear theory power spectrum, but the density field is actually this one. To me, this is working.
Yeah.
If you just want to fit the data, maybe it doesn't work. But then this motivates, for example, well, okay,
Okay.
you can make this work. I get it. Yeah.
Qualitatively, then you mentioned before the simulation provides the field. That should kind of look like what you just said is something similar to a normal simulation, right? Like it predicts it predicts, it returns basically the input power spectrum that you get.
Mhm.
And then has like a better distribution of the densities in order to get covariance and so on. Is this something similar?
Yes, but notice that the log normal doesn't actually have any physical information about the initial phases that you have.
No.
So in some sense, this is better because it's much more correlated.
It's for me to understand
Right,
how
yeah.
it works.
Yes. Something else that's kind of interesting, which I can comment on later, but what this also already shows you is that this maybe motivates a much better way to do sample variance cancellation simulations than pairing and fixing. So this is one of the papers that I wrote, because basically you can just use the Sadovich approximation, use the fact that it's exactly solvable to cancel any sample variance that you had in this simulation, because all of the sample variance comes from the cosmic noise that you put in by hand. These have the same exact random phases. So you can get like millionfold cancellations in sample variance by exploiting this. Okay, so the second thing, I managed to do one calculation. I'm actually very happy. I didn't think I was going to get there. So thank you all for your patience. In the last 10 minutes, let me just very quickly point out the following, which is the second step that we need, which is how can we actually encode this tracer population really at the level of the initial conditions. And so the way that this is done, and I'll guess it's over there. One of these is much better than the other. Okay, so the only thing that I'll say then is how do we actually get bias tracers implemented in this description? And it turns out that it's really quite simple. So what bias tracers are is basically some claim. You're really failing me now.
There's another one.
I know, but this one was fine. They're so temperamental. I don't understand. Okay, so you're saying that the number density of halos in your Lyrian picture, right, in our Lyrian coordinates is basically equal to some non-trivial function of the Hessian of the gravitational potential. Also at the same time, at fifth order, you get these time non-locality effects that are kind of non-trivial, but you're basically doing some Taylor series in the scalar quantities that you can build from this. So the trace gives you the density field, that gives you linear bias. It's the first power that you can write down, so on and so forth. Lagrangian bias, exact same thing. You just say, actually, what if at the very initial conditions, my very early on tidal field already contained all of the information that I need to assign labels to this distribution, such that when I let my dynamics play forward and everything move around, I get my halo distribution at the end of the day. So this is a slightly more like artificial, maybe a mathematical construct, but at some scale, maybe at the very small interior dynamics where my particles have been kicked around a lot by n-body forces, this won't work. But sort of on aggregate at very large scales, this should be an effective description of what's going on. And so what people also normally do is point out that this is always valid up to some scale R, which will depend on the tracer population that you're looking at. And then you can expand this the same way. And so really this is going to be basically the average number density of halos plus what we now call this B1 Lagrangian times this exact matter distribution here, which is just the trace of this in suitable units. Your second order Taylor series term. Some term that will look like the tidal tensor. So I'll define this in a second. Where Sij is just the trace-free part of this Hessian. So this is di, dj. Right? And so the basic idea is just if you take this trace-free part, then this is a tensor, so you have to square it to get the first scalar that you could write down. I had defined everything at some smoothie scale, and so what you can also show, and I won't do now, but is that this is equivalent to defining everything like this, but then also getting a new term that looks like this, and some higher derivative correction. And I could just do this order by order for a very long time. And I finish with something which is just some part that is fundamentally uncorrelated noise-like contribution, physics that is, really beyond anything that I can hope to get. It just, yes.
Nick, this is where I get confused, for instance.
Uh-huh.
The part that you were doing before, we have matter participation.
Yes.
Does that epsilon term account for not having the trace server?
Yeah, that's a good question. To some degree, yes, but you're also basically here you're basically saying that this is fluctuations on scales like very small compared to R that somehow modulate my number density of tracers at the end of the day. So in Lagrangian structure formation, you have to make a little bit of a stronger physical assumption that there exists some proto-tracer density that has its number density conserved to give my final late time distribution of halos. That's not to say that if I were to take all of these halos and walk back their merger trees and then look at that distribution, that is the right proto-halo tracer density, because that's super not conserved because they merged a lot. So this is more of like an artificial construct saying that you can identify in the initial conditions.
So guess of how of the big clusters and so on.
Yeah.
More or less like that.
Yes. Some effective tracer that looks like the thing at the end of the day that I would get. And so, yes, so as Guilherme was pointing out, this is actually kind of a stronger physical statement. Order by order in perturbation theory, you can recover the same thing that people do in the Eulerian case. But the whole point of this talk is that we shouldn't be doing things order by order. We should be taking this picture more seriously.
So Nick, can I
Yes.
ask a question before you go on? So this idea here, it looks very similar to what you would get by making a similar expression, but in the eigenvalues of the tidal tensor field, then you computed also on some length scale R, right? I mean, it has to be equivalent to this. I don't know about the delta square, number square delta, that I'm not sure, but the other ones,
Yes.
No.
Yes, I think that's right. I think the eigenvalues of the tidal tensor, though, their description is a little bit less trivial because like the density field is going to be the trace of the eigenvalues in the right frame. But at any point, you have to rotate into the eigenframe of that at that point, right? Like if the tensor is off, like you can only diagonalize it at that one point in the field. There's no continuous transformation that diagonalize, like there's no one global transformation that diagonalizes the tensor everywhere.
Right,
Right,
but
I think that
so what?
maybe the
What you
Well,
You just look for a given scale, you
Mhm.
you get your tidal tensor
Mhm.
there, it's a
Mhm.
matrix, you
Mhm.
just look for the eigenvalues of that. What will
Yes.
be different in each place? Why does it matter? Perhaps I missed that.
Oh, I guess just because if you want to do like summary statistic calculations, these statistics are a little bit more well understood than, but
Yeah.
yeah.
Right.
But in principle, I mean, in principle, you could actually basically, really do like try to figure out a mapping between what is my Lagrangian bias of a sample saying versus what are the eigenvalues of the tidal tensors of the proto-halos that I've identified with that bias saying. That's definitely something that, and some people have been doing this for halo spin actually. It's very interesting, but okay.
One stupid question. So in the Eulerian picture, normally we assume 2 degrees of freedom there, phi and phi v for the velocity. Here you only have phi, right? Because you have one single.
Yeah. So this is something, yeah. So in LPT, the velocities are always just given by the displacement, by the time derivative of the displacement field. So they're not like this kind of different degree of freedom. I think you can always generate via non-local contributions through like Galilean-like terms, something that functionally looks like 5e. Because like the G3 Galilean is like some 5e squared minus 5g squared times delta, right? Or something like and you can show that the basis, so the way Fabian likes to write it, right, is that really the basis is these tensors Lij, which are di psi j to nth order in perturbation theory. And so if you just basically take nth order displacement vectors in the Lagrangian frame and then build the right matrix products, you generate the same basis as the Eulerian one. It's just re-expressing the tensors in the right. re-expressing the operators to look the same. So I guess with my remaining 5 minutes, I just wanted to point out how do you actually implement bias tracers here. And so the point is that people assume now something very similar, which is number density conservation. But now you say that my distribution of halos at my very early times in some patch will roughly evolve on these scales into my halo distribution at late times. Oh, sorry, at late times. And so that same game over here, you now get a slightly different expression where whatever this function f is,
Sorry, I fail to see why this has to be conserved, given that they merge and so on. Why is this?
Yes.
Density, yes, but number of halos, why?
It's it doesn't. So this is like kind of an ansatz that you're making, but what you're saying is that you're identifying. You have your late time halo population, and you're identifying in the initial conditions a population of roughly similar number density. So imagine the following, right? How if I just took all of my halos at late times and moved them back and figured out where they were, the number density is conserved and they just got moved.
I guess that like within these sunsets, the volume covered by the regions of the particles that are the protohalos don't overlap between them. Can they overlap?
I would have to think a little bit more.
Well, we have to move somewhere, right?
Yeah.
You can just go this way and that way.
Yeah, so that's
Yeah.
why I was.
I think they can overlap.
They can.
Uh,
Where to the two halos they go? They overlap
so you're saying the late time or the early time can't overlap?
early time.
Yeah, I mean, you would have to see. I mean, in principle, you have late time exclusion. Okay, I think they won't just because structure formation makes things go closer to each other. And so if you take two halos that are close by, and you undo structure formation, they'll go farther away. You could have some patch that moves such that they have overlap, but there's some degree at which exclusion might also apply in initial conditions. But this is, I think, yeah, I wouldn't make any definitive claims about this. So I will just point out the following, just because I'm out of time, and this is the second calculation that I wanted to make. This looks very similar to this, but now something very interesting happened. All of the dynamics, all of the time evolution of my system are still encoded only in this Dirac delta function. And all of my structure formation, all of my galaxy formation physics is encoded in the initial conditions. And so actually the Lagrangian picture in some sense very explicitly decouples time evolution from structure formation. And so if you have some magic wand that lets you go back to the time of the CMB and look at the density fluctuations in the very early universe, you could point out by hand where all of our galaxies are going to end up being. Which is honestly not too dissimilar from what like Joe Silk was saying all the way back in like the Big Bang nucleosynthesis era. And like yeah, I mean this is kind of very powerful. And
Can you say again? So
Mhm.
so the delta function encodes the time evolution.
Exactly.
And F is bias expansion.
Is the bias expansion. And so the bias expansion, right? The dynamics don't actually factor into this at all. And so in some sense, I can just write this completely independently of this. Any tracer population a priori, I could just find what is the right F that will map its late time, map it back to the initial conditions by some deterministic process. And so the only comment that I will make, and I guess this is where I will stop. I mean, I can keep going, but I also know it's lunchtime already, is that the correlation functions get very difficult. And the reason now is because, for example, if you just try to do in linear bias only, you get something somehow nastier than what we had before. And so notice now, not only do we have this resummation, but we also have the new correlation functions that show up down here in the bottom beside this, which are coming from the bias expansion things that we sourced. So the general structure, so an LPT bias correlator is just generically going to be given by something slightly nastier. where you now have to evaluate not just this term, but also figure out what to do with this. However, not all is lost. If you're afraid of the math and you don't want to do these calculations because they seem very difficult, this also points out that the expansion that I wrote down for F breaks down on some scale R. I had mentioned that whatever perturbation theory I did for psi breaks down on some scale related to the dispersion of these displacements. And so if I just ran an n-body simulation of dark matter only, I won't have this scale breaking down. My size will be exact. They will be fully correct. And so then what I could imagine doing instead is just saying, oh, I don't want to do any of these calculations in practice. I'll just use this that comes directly from a simulation. I'll build this bias expansion in a simulation. I can take my density field. I can square my density field. I can take my tidal field. I can identify exactly what all of these quantities are. And then I can just displace them by whatever comes from the n-body simulation and get all of the terms in the bias expansion at late times, the entire field level density distribution. And then I can just calculate these power spectra by just measuring the power spectra between these things in a simulation, which is exactly this hybrid Lagrangian scheme that Matteo introduced last week. And then what you fundamentally get is this view of the universe where now your n-body simulation, or so your dark matter halo distribution is just given by some basis fields, basically, that are everything that symmetry lets you write down, some coefficients, but that's okay. So I won't go through this calculation, even though I think it's very interesting. But if you could do this calculation analytically, what's really nice is that any summary statistic coming from this simulation-based scheme, where perturbation theory is valid, should match what you measured. And so what this also means is that the coefficients, because they describe the same population, you can basically use perturbative calculations in regimes where the perturbation theory holds, for example, redshift space distortions, which have a cutoff that's different from this displacement thing and different from this R. But for other things like a bispectrum or some field level inference or for some simulation-based inference, you can just use the outputs of this suitably matched with the same free coefficients. And so this also paints the way to sort of, do away with at least this cutoff scale and solve this problem of, very bespoke summary statistics that are higher order that are very difficult to compute in perturbation theory. But this is also very fun to do. So I'll end here, I guess, and happy to take more questions.
Thank you.
I have just another thing that I try to understand always is that so in n-body simulation, we're not actually solving for the displacement field. So for instance, there, we already do this decomposition, so we're always solving for psi. So we can trust that X is truly the Q plus psi. So in n-body simulation, psi is maybe not be psi over t. You see?
So this gets into some, it's a little bit technical, but this depends on the pseudo initial conditions that you used. So if you use just lattice pseudo initial conditions, then there's a one-to-one mapping between